All right, this is the Unit 9 test review number 12. Solid sodium carbonate, Na2CO3, reacts with sulfuric acid, H2SO4, to produce CO2 gas, which is carbon dioxide gas, according to the following equation. So sodium carbonate and sulfuric acid yield the carbon dioxide plus water, and this is sodium sulfate. This is a balanced equation. We've got two sodiums here, one carbon here, one carbon here. 3 plus 4 oxygens is 7 oxygens on the reactant side. 2 plus 1 is 3, plus 4 is 7 oxygens on the reactant side. 2 hydrogens, 1 sulfur, 1 sulfur. So the equation is balanced as is. All right. Now, during an experiment to produce carbon dioxide gas, a student recorded the following data. We've got this data here: pressure, volume, and temperature for carbon dioxide. Our pressure is in millimeters of mercury, our volume is in milliliters, and our temperature is in degrees Celsius. How many moles of carbon dioxide are produced? All right, so this is an ideal gas law problem because we've got pressure, volume, and temperature, and we're looking for number of moles. We got a couple issues here, though. Our volume is in milliliters, and we need it to be in liters, and our temperature is in degrees Celsius, and we need it to be in Kelvin. Those are the things you need to remember when you're dealing with ideal gas, that, any gas stuff, remember, temperature always has to be in Kelvin. And then because of our gas constant, which we get from our formula chart, we need to pay attention to the units that we have. We have units of millimeters of mercury, which means that our gas constant also has to be in the same units. So I'm going to go ahead and write the gas constant down that we need to use. The R value that we're going to use matches up with the millimeters of mercury, which is the 62.4. Now, the units are liters, millimeter of mercury per moles Kelvin. All right, so this is why I said we've got some issues here. Our volume that we're given is in milliliters, but if you look at the gas constant, it's in liters, which means that we need to convert our milliliters into liters. To convert milliliters into liters, remember there's 1,000 milliliters in a liter, which means that we need to divide this number by 1,000. So when you divide 29.65 by 1,000, that's like moving the decimal place over to the left 3 places. So that means our number is 0.02965 liters. Okay, so again, that's just moving the decimal place over 3 places. So if we look, 1, 2, 3 gets us back to 29.65. All right, and then temperature, remember to go to Kelvin, we always just add 273 to our number, and 25.5 plus 273 is 298.5 Kelvin. Okay, so those are all of our givens. Instead of writing the givens down again, I just fixed them up here in our little table that was kind of already made for us. Our unknown comes from the question right here at the end. The question right here at the end says how many moles of CO2. So remember, moles is in the number of moles, and of course the units are moles of CO2. This is the ideal gas law, so that's PV, PV equals nRT. All right, so at this point we just have to substitute in our numbers. Our pressure is 708.1. Our volume is, remember, you got to use the liter amount, 0.02965. Oops, excuse me. Let me fix that. Sorry guys, my dog's bouncing on my arm trying to get me to pay attention to him. Is equal to, that's equal to our number of moles, which we don't know, times our gas constant, 62.4. Remember, it's very important to use the correct gas constant according to your pressure units, and our temperature, which is 298.5. Remember, you always have to use your temperature in Kelvin if you want to get the right number on these. All right, so simplification. First thing that we need to do is we need to multiply these two numbers together, get a number, multiply these two numbers together, and get one number. So let's go ahead and do that. All right, so 708.1 times 0.02965 gives us, oops, get my pen back, 20.995,165. And remember, you don't want to round these off too early or you get error in your answer. And 62.4 times 298.5 is 18626.4. All right, so now solving for n, if we look at this, n is multiplied by this number, so opposite operation is to divide. So we're going to want to divide both sides by the 18,626.4. That cancels it out on the right. So our number of moles is equal to, so on the calculator you're probably going to get this, 0.00112717. Alright, this is a very small number, so it's really better to write this in scientific notation. To write this in scientific notation and looking at our significant digits all at the same time, if we look up here, we've got 4, 4, but our temperature only has 3, our gas constant only has 3, which means we need to take our final answer to 3. So that's right there. Okay. So that rounds this to 0.00113. Okay, now taking this to scientific notation so that this is written more appropriately. 1, 2, 3. We need to move it over 3 places to get the decimal after the 1. So this is 1.13 times 10 to the negative third moles of CO2. Okay, and the only reason why we're writing this in scientific notation is because it is very small. Remember on your calculators, if for some reason on the STAR test they give you answer choices that are in scientific notation, but in your calculator it doesn't give it to you, that you can hit that second and then the DRG number, or DRG key, which is the degree key, and then scroll over till you get to SCI and select the SCI, which is scientific notation. And then when you want to go back to just your normal mode, you hit the second degree button again, and then you scroll back to the normal one, which I think is FIX. I can't remember for sure, guys. I don't have the calculator in front of me because I'm doing this from home. But you want to go back to the normal one so that you don't always have it on scientific notation, because otherwise it's confusing when you look at your numbers. All right, so that's number 12.